you imagine you come in and all you know is that you have a value S and a value I that have this property, right? S is 1 plus 2 plus 3 up to I. And you want to make progress while maintaining the loop invariant. So you see that you want to increase I by 1, right? So that's reasonable to increase by I by 1. And if you want to, now you have to update the S so that it sums not just up to I, but sums up to I plus 1. And so then, to do that, you have to add on to S I plus 1, right? But this is wrong because this is only adding on I. People see that bug? And if one wanted to be more formal, one has to differentiate between the old value of S and the new value of S, right? And hello. So establishing the loop invariant is wrong too, because if you plug in these values, you don't get that. And it turns out the exit condition is wrong as well, because this exit, I don't like the while bit. I like it better when you have exit when, because then it's more clear what the exit condition is, right? So it exits when little I is bigger than capital I, right? And if it's bigger than capital I, and this is your loop invariant, then we've summed too far. So that's just going through that example again. And as it turned out, I made this code so that it had as many bugs as possible, and in the end, the code actually works. The only thing that was wrong with it is the loop invariant. If you change the loop invariant, everything else would be fine. All right, so at the end of last term, I made up this other example, and it's kind of a weird example, but I was marking exams, and lots of people were making the same mistake, and we're can't really do the exact same mistake that people were doing in the exam because we're not there yet. But so this is sort of a simplified version of it. So here's, it's about as simple of an example as you can come up with. You start with I equals 0, and you want to output, the number 131, and you want to step by increments of 2, right? So what people would say, well, a loop invariant, I is increasing. Is that a good loop invariant? No, why not? It's an action, right? So we don't want that. We don't want an action, we want a picture. So what people often will do is they'll have this as they had sort of they'll write something here, but it's really vacuous, right? It doesn't mean anything. And here you have your step, and here you have your exit condition. So let's go through our various things and see if this is a good algorithm, right? Maybe you can even sort of think ahead about what's wrong with this algorithm. Anybody want to buy right now whether this algorithm works? It doesn't, right? All right, so something's clearly wrong with it. All right? So what's wrong with it? Do we establish the loop invariant? Well, there is no loop invariant, so it's pretty trivially established, right? So people say, oh great, I established the loop invariant. That was good, but it had no content. Right. Similarly, do I maintain the loop invariant? Sure, you're maintaining it. It has no content. Right? And then, assuming I have the loop invariant true, and I have the exit condition, right? Do I get the post condition? Yes. Yeah, so this one is really good too. And let me tell you right now, I will fail you if you ever have your exit condition be the post condition. All right? Because you're missing the entire point. You know what I'm saying? If you're coming up with an algorithm and you have some post condition and you just simply write your exit condition to be that you've solved the problem, then then you've just sort of transferred the error, the solving the problem onto will you stop? Right? So here, if you're following what I'm saying here does this happen? Well, if you assume the loop invariant, which doesn't give you anything, if you assume the exit condition, right, it automatically gives you the post condition because they're the same. People see what I mean? All right, so do we make progress? We certainly make progress, right? We increment I every time, right? And we didn't start off infinitely far from where we're going, so everything's good so far. What's going to go wrong?
All the numbers will be even?
Yeah, but in the math, what goes wrong?
The exit condition is never true.
Yeah, the exit condition is never true, right? The problem is this one, that if your measure of progress goes to 0 or goes up, you won't exit because you sort of jump over the exit, right? So that's what goes wrong, right? So now the reason I created this example was to illustrate you don't want the loop invariant. Oh, sorry, what am I saying? You don't want the exit condition to be the post condition, right? Because then clearly when you stop, you have solved the problem, but we don't know if you're going to stop. Right? But now once we have this example, it's actually trickier than you think to actually fix up this example. Right? So we need a little bit more about the loop invariant. Right? We want eventually, you know, there's this sense of even and odd, right? So we want things to eventually be odd. So let's stick in our loop invariant that we want it to be odd. And then how do we establish the loop invariant? You know, we got I equals 0. Now we want to establish the loop invariant as easy as possible. You add 1 to it, right? Right, but that's pretty good. All right, and now how do you maintain the loop invariant? Well, this is pretty easy, right? Oh no, this here. If we have the loop invariant true, and the loop invariant says I is odd, the exit condition says that I is big. Oh well, we fixed that one, the exit condition by making it greater than. I didn't say that. Greater than equal to, right? So now do we get the post condition?
So I had a question. In the previous slide, you had I equals 1. Is that code A? Like it goes into code A, or where does it go?
The I equals 1? Oh yeah, that's code A.
Code A.
Right, that was establishing the loop invariant. Exactly. All right, so now, is this going to work now? If we know that the loop invariant is true, I is odd, and the exit condition is true, does that follow that I equals 131? Not really, right? But so that's kind of this extra. Usually we don't have this many kludges. This one has this extra little kludge that you don't want to miss it. So we'll add on to the loop invariant this extra thing that we haven't gotten too big. Right? That's a little kludgier than we would like, but whatever. And then we have to prove that we maintain it. And this is gives you an example where you say, hey, the loop invariant, right, we're at the top of the loop. What do we know? The loop invariant is true. It says it's odd, and we're not too big. That's our loop invariant. The non-exit condition gives us that, well, actually we're smaller than 131, and we added 2. So that gives us both that we maintain the oddness because we added 2, and that we haven't gotten too big.
So when we have the exit condition that I is greater than or equal to 131, why do we need that in the loop invariant that I is less than or equal to 1?
Why do we want this part here?
Yeah, like why do we need that if the exit condition already has something that, like, why are we doing it double? Why is that needed?
Well, we need it. All right, so if we know that I is odd, and the exit condition gives us that I is big, that alone doesn't give us that I is 131, because it could be 133.
So it's 133, it's not supposed to exit, it's only supposed to exit 131.
I mean, formally, we simply want to say from the loop invariant and the exit condition, right? And the code, we want to get the post condition.
Okay.
right? So, what we really needed is, well, we exited and we, you need a little bit extra in there, and it's this, as I say, this is just little clues. We put in a little clues that, we haven't gotten too far. Don't worry about this example. The point about the example was not to have the extra condition be the post condition.
If we don't use greater than or equal to for the extra condition, instead just put the equal sign there, and then we don't need the extra I smaller than 132, right?
No, you don't. But then you have the danger that you're going to jump over it and never exit. Right? I always get nervous when I'm writing code about saying exit when I equals 131 because, there's this, you're much more likely never to exit.
Okay.
So, if you do that though, if the greater than or equal to, and you say, like you said, it might just never exit.
Right.
But if you put the equal to, then you could exit and have the wrong post condition somehow. By this sort of same logic, yeah, you've exited, but now you've got the wrong answer.
Right. Right.
So.
Right, exactly. Well, that's why we had to be extra careful that we had the right answer. And I'm sure you've all, in some ways this is a dumb example, but I have certainly in my undergrad days spent a lot of hours trying to get the answer to be 131 and not 132. It can be surprisingly irritating. And loop invariants can kind of help you with that. Anyway, so we want to think about how to come up with a loop invariant for your problem, and after having given it a lot of thought, I've narrowed down the loop invariants that we use typically to be these 5 kind of cases, and usually these ones are the ones that happen the most. And so we're going to give examples of these types of loop invariants, and that way when you have a new problem and I say, hey, come up with a loop invariant, the first thing to do is to think about these loop invariants and see if they work for you. All right? So the more of the input one, your input for your problem consists of a bunch of objects, right? And our loop invariant is going to say, I've read the first I of the objects, right? The algorithm will read one at a time, but you've read the first I. What do you think we want the loop invariant to say now? Any idea? Well, what we're going to do is we're going to pretend that this prefix is just like when we were doing, in some course or other, we did finite automatas. Right? This is going to be like a finite automata. We pretend that what we've read so far is the entire input. Right? And if this was the entire input, then what have we produced? We have the solution, if that were the input. Right? Does that make sense? And we have a little extra, maybe we carry a little extra information just for good luck. So this is what the loop invariant will be, and you can, for many problems, you can assume that. We can try this loop invariant. It says we have all these inputs, we've read some of them. We think about what we've read as being the entire input, and if that was the entire input, then we have the solution. Right? So this is just an example of a finite automata, right? If you're trying to compute some weird property of the string, as you go along, you have the answer, and the answer is stored in what state you're in. But we're not going to worry about that. All right, so then we want to maintain the loop invariant. How do you maintain the loop invariant? Is you read the next, you need to make progress while maintaining the loop invariant, right? So to make progress, you read the next object, right? And now how do you maintain the loop invariant? What do we have to do?
Pretend that that's one.
Assume that's all the input.
Right?
And then assume that is the solution, and we got it.
Not assume it, we have to make sure it is.
Oh.
Right? This little, you go away. Go away. Okay, there we go. Alright, so we pretend that this larger thing is the input, and then somehow we have to take the solution that we had before and somehow extend it into a solution for the longer input, right? And we also have to update our extra information. Does that make sense?
Do we use the old extra stuff to figure out a solution? Is that what that is for?
Yeah, we're going to have examples where you need this extra stuff to help us. All right, so our measure of progress is clearly how many things we've read in. And all right, so now what's our exit condition going to be, and how is we're going to get our post condition?
Exit condition is that there's no more objects.
Right, the exit condition is you read everything, and the loop invariant says that we have the solution. So we're done. Right, does that make sense? All right, so here's an example, insertion sort, right? The loop invariant would say, I've read some of the numbers, right? And what do I have? Oh, I remember these slides kind of moved. I don't know why the solution's over there. The solution should be over here. I read these numbers and I have a solution, right? There it is. There's the solution, right? And so that's what the loop invariant says. And now how do we make progress while maintaining the loop invariant? So you read the next number and you have to insert it in there, right? You find where it goes and you get, right? So that's insertion sort is a classic example of reading the loop invariant, which is reading more of the input. Does that make sense?
So we don't have to measure how many objects are left to make progress. We just check our solution to check we've made progress.
Well, we need two things. You need a loop invariant, which is what we said, and you need a measure of progress.
Okay.
And so the measure of progress will be how many numbers you've read in, or how many numbers left to be read. And so every iteration you have to make progress while maintaining the loop invariant. So you make progress by reading the next object in. But when you read it in, then you have to update the loop and maintain the loop invariant. All right. So on a lot of midterms, I've asked, okay, I've explained this, more of the input idea. Tell me what it is. Tell me what the loop invariant is. And so I got this answer a lot. Each iteration considers the next input item. So is that a good answer? Why not?
When you reach the end, there's no next input?
No.
It doesn't say that you have to maintain the loop invariant.
It's what?
It doesn't say that you have to maintain the loop to the solution.
Yeah, and first off, it's an action, not a picture. Right? I'm saying, what is the question is, what is the loop invariant? And this isn't a loop invariant, this is an action. Right? All right? A loop invariant needs to be a picture of the state, not an action. All right, so people say, well, we've considered the ith input. All right, well, that's kind of a picture. It says that something that's true. I've thought about the ith element, but does it say anything? No, it doesn't say anything. Right? It doesn't talk about the previous items, for example. All right, so it could say, well, we've considered the first I items. Still doesn't say anything, right? All right. So here we say, I've read in the first I objects and I have a solution for each of them. Now think about this, everybody. How many people like this answer? How many people don't like this answer? How many people never put up their hand ever? Good. This is not a good answer. And somebody want to tell me why it's not a good answer?
Because you have I answers.
You have I answers, right? And how many do we want? One, right? So this is implying that for each number I have an answer. Like for example, in the sorting one, okay, I've read all these numbers, and each number I've sorted. Right? I sorted the 3, and then I sorted the 4. Right? That doesn't mean anything. So that's not what we want. Right? We think about the whole thing as the input, and we have a solution for them. People good with that? This is one thing I try to do. It's partly to make the teaching, to help you guys learn better every year, but part is to relieve my frustration. So after I've spent 2 or 3 days marking a question wrong 50 times, I relieve my stress by making up slides. All right, how about this one? We have a solution for the prefix consisting of the first I elements. Does that sound good? Yeah, I'm pretty good with that. And we have extra information. And if you miss the extra information, I don't think I was so relieved that you got it mostly right that I don't think I even forgot one. All right? All right, so here's another example. All right? It's a pretty easy example. I want to find the largest block of ones. Right? This is a block of ones, and this is a block of ones. You know what I mean by block of ones? I'm going to find the largest ones. So, there's a block of one there, right? Right, so we're gonna be like a DFA, deterministic finite automata. We're gonna read the input characters one at a time, and we're gonna remember just enough to remember so that we never want to go back again. Right? We remember enough so that we have the answer when we stop. All right. So what do we have to remember? Right. So we need the largest block so far. Suppose we've read this and right. Right. We certainly need to know the largest block so far. Everybody good with that? So how do we maintain the loop invariant? Well, you read the next character and you redetermine which is the largest block, right? So, okay, so far so good, right? We read the next character. We read the next character.
Wouldn't that loop invariant action, like read the next character and redetermine?
Oh no, this is maintaining the loop invariant. This is where he's stepping. The loop invariant is that we've remembered the largest block so far. All right? So, can we maintain the loop invariant now? Why not?
Because we can't calculate which one is the largest block.
Yeah, because we don't have any information about this. Right? People see that? So what else do we have to store? Right, exactly. We have to store the size of the current block. And this is an example of extra information, right? This is, in some ways, we've read this so far, and this is the answer. That's the solution, and the extra information is kind of what we're working on. That make sense? So now we're good. We read that one, and the current block gets updated, right? And the current block gets updated, and the current block gets updated, and then oops, then we shift over the largest block. Everybody's done this code before, right? Yeah. And it's just an example of, what we need in our loop invariant. Everybody good with this example? All right, more of the output is kind of more obvious. The output consists of a bunch of objects, and what do you think our loop invariant is going to be? Pretty straightforward. We've outputted some of them. Right? And then how do you maintain the loop invariant while making progress? You output the next one, right? And your measure of progress is the number you've outputted. And when you've outputted them all, then you're done. So here's an example. I think we should ignore the blues for a minute here, but if right, so if the input was these numbers in purple, then that's the output, and the loop invariant says that we've produced some of the output, right? And then we should have crossed off the guys that we've produced already. And now for selection sort, what we do is we have to produce the next one. And how do we find the smallest guy and we put it there? Right? Does that make sense? So remember about those crosses. Those were wrong last time I gave this. And when you've outputted them all, you're done. All right. So So here we have two examples. And one, if you just simply say sorting and I want to do more of the input, automatically you come up with insertion sort. And this one, automatically you come up with selection sort, right? And it'll be you're amazing how often, if you have a new problem and you just do one of these, it just does your problem for you, right? Now the next one we're going to do is narrowing the search space. And we're going to give some examples of narrowing the search space. So it's a binary search. We all know binary search here. The problem is the precondition is you're given a list that's sorted, and you're given some key, and our goal is to find it. Find an index where it is, if it's there, and if it's not there, to say, hey, it's not there. Right? So our loop invariant is going to be what? Is we somehow narrow the search space. Here the loop invariant is, we've narrowed down the region down to some, to the smaller region. And what do we want to say about this sublist?
That it contains, it might
It contains key.
Those are both pretty good. It does contain, well, what's the problem with that? It might not be anywhere. It might contain, it's a little too vague. But you're on the right track.
If the answer's there, it's contained.
Exactly. If it's anywhere, then it's in there, right? If the key is contained in the original list, then it's contained in the sublist, right? And then, how do we make progress while maintaining our loop invariant? Well, you do binary search. You cut it in half. You look at compare it to some item, and if the key is smaller, you go over there. Otherwise, you go over there. Everybody knows this, right? All right. And then the size, how do we make progress? Is we keep making the size of our region smaller. In fact, it gets smaller by half each time. The initial, how do you establish the loop invariant to begin with? Is you make your search area the entire space, and then the loop invariant says, if the key is contained in the original list, then it's contained in the sublist, which is the original list. So it's sort of vacuous, right? Everybody good? And the ending condition is you stop when we've narrowed down to size 1, or actually size 0 would work too, right? You narrowed it down to size 1 or 0. And it says, well, if the key is contained anywhere, it's contained in this little list. So what do? You look in there and see if it's there. And if you find it, you're happy, you know where it is. And if you don't find it, then you do the modus ponens. Say if it was anywhere, it's here, but it's not here, so it's not anywhere. Right, people got that? All right, this is just what I said, the modus ponens. If it's not anywhere, if it's not here, then it's not anywhere. The running time, everybody should know, this comes up a lot. You start with n, you divide it by 2, you divide it by 2, you divide it by 2. How many times you divide it by 2 before you get to something less than 1? Log n times, right? So that's the number. That's the running time. Everybody with me here? And there is the outcode. You've all seen it before. All right. Now, here's a problem. Right? The problem. I think I showed you the slide already. Right? They asked people to do it, and 80% of them got it wrong. Right? And one thing actually I find interesting about this number here is we're going to see that there's some little ways that you could go wrong this way and you could go around this way. And if you think every time you do them randomly, then you're going to get it right probability 1/4 of the time. So this is approximately what people why do this number here is because people flip the coin. Do I do this or this? And all right, so let's be more precise and see where things can go wrong with your loop invariants. All right? So we need a value, we need a sub region, a sublist, and it needs to be defined by some I or some j. Now, does it include the I, is it from I to j inclusively, or just, what I mean? Is this guy included? Or is this guy included or not? Does it matter? What do you think? Do you think it matters whether you do this or this? Why does it matter?
Because if you should include it, and that's the one that you're searching for, and you don't include it,
Right.
and you're just going to keep narrowing the search that doesn't exist.
Right.
You'll never find it. Which
And
is
it-
the wrong answer.
What?
Which is the wrong answer.
Right. Right. Well, we're going to come up to what you're talking about in a minute. But right now is just our definition of the sublist. I claim it doesn't matter, right? But I'll tell you something that does matter. That you're consistent. That you know what your definition is, right? This is kind of your typical definition to do this. But if you wanted to do this or this or this, it doesn't matter which you do, as long as you're very clear about what you're doing and that you're consistent throughout the program. And not only are you consistent, but the guy who comes and modifies the program a few years from now also knew what you were doing and is consistent, right? That's what matters, and that's why it's important to be clear, right? So when you're stating the loop invariant, you need to state, well, the sublist is from I to J exactly or something. All right, here's another thing. You know what you do is you find the middle guy, right? And if the list is of odd length, the middle guy is in the middle. But when the list is of even length, do you go for this guy or this guy? Does it matter?
Not really matter.
You wouldn't think it would matter, right? The world is symmetric. If I turn myself around, it shouldn't matter. All right. So here's another. So we split it like that, and now we're saying if the key is less than or equal to the middle guy, this is the middle one, then we go this side, and if it's greater than the middle, then we go that side. How does that look?
You didn't do the equals.
Okay, it equals over here. Less than or equal. Now that was another point is should you have a third case to say if it's equal? Right? You could do less than one case, greater than one case, and the third case is it's equal, then you stop. Back in the day when people really needed to sort fast, when computers were slow, they did lots of analysis and they discovered it's actually, you waste too much time doing the equals. You want to have two cases and narrow it down. So people think this code's going to work? How many people think it works? How many people think it doesn't work? Why do you think it doesn't work? Just flip the coin? Good point.
You're excluding the 25 itself. That if that 43 was a 25.
Exactly, you'd be lost. Right, exactly. So suppose that you look, and it is a 25, then it says that you keep this side, right? But you've lost your 25.
No, because the list already sorted. So 25 cannot be.
No, but I mean, all your numbers are different. It's not just a 25 here. Change this to same list. Change this to a 43. Right. So this is a 43. You say, oh, it's a 43. So the key is less than or equal to the mid. So I keep this side, and I've lost my 43. You with me?
No.
No. All right. So suppose we're searching for 43.
Yeah. So if the key less than equal mid, so the key should be 43, and the
Right.
mid also will be 43.
Right.
So the 43 will be in the small size.
Right.
Yeah. So
Right.
we get it.
Yes. So we keep this piece.
No. We need to add one.
Oh no, but this is the code. You can't correct my code. I've asked, does this code work?
if you in that case you already changed the condition.
Because it takes the left side.
Yeah. So
Left half.
I asked, should I take the left side? You know, which one? I'm searching for this one, and then I split it like this, and I split it like this, and I asked, does this code work? This code does not work.
Yeah. No.
Yes. Right. Exactly. This code does not work. All right. How can we fix this code?
Change the equals.
Right. we can put the equals over there. Right? That's one way to change it. Right? The other change is we split it one to the left and then have, right? So there were two options and you had to get them, you know, either one would have been fine. All right? So here's another option. Let's go one further over. Right? We like this. So let's go over here. Does that, everybody happy with this algorithm now? Everybody think this algorithm works?
Yes.
Looks pretty good. You know, we just, you know, our algorithm didn't quite work, so we fixed it, we fixed it till it worked. Now, all right, I think we got a new bug. All right, so what we did here is we narrowed down, you know, where we're dividing here. But here, if we had two items, then the split becomes here. Now, does this code work? No, because, why not?
It will keep on running.
It'll run forever, right? Because if you have a list of this side and you split it here, then you have a list of this side and you split it here, right? It can run forever.
Why does it search that way and not in the middle of the sublist?
Oh, I'm just looking at various bugs. People didn't like it here, so I put it over here to fix it, and that created a new bug. All right, so yeah, so you have a choice whether to do this or this. And you have a choice of whether to do this one or this one, and you have a choice whether, you know, you subtract or not. And anyway, there are various algorithms here, and some of them work and some of them don't work, and the probability of getting it right I've worked out once, so it came out to be, you know, if you did them all randomly, then it worked. Anyway, what's the moral here? Is you know, it's really good to use the loop invariants. You know, have a really clear loop invariant. Make sure that your loop invariant is precise, and make sure that you always maintain the loop invariant and that you always make progress. So you know, what I do is I think about, okay, what about my first iteration, my first couple of iterations? Am I getting going? Am I making progress? Am I maintaining the loop invariant? You know, I think about a typical input in the middle iteration. You know, after I've iterated a lot, do I make sure I'm making progress? And you know, and as you're ending, you know, be careful. You know, when it's down to size 2, do I really, you know, check if inputs of size 3, 2, 1? You know, you check all these various cases. All right. Oh. Okay. Here's the same sort of thing, but for binary search. Everybody knows the binary search algorithm. The precondition is we have a binary search tree, and we want to, and some key, and we want to find it. What's the property of a binary search tree? Is that for any node in the tree, everybody in its left subtree is smaller or equal to it. Everybody in the right subtree is bigger or equal to it. Everybody remember this definition of a binary search tree? Here. All right, so what's our loop invariant? It's going to be the same. Is that we're maintaining a subtree. We have our finger on a node here, and what our loop invariant says is that if the key is anywhere in the tree, it's somewhere in this subtree. All right, everybody with me here? Everybody good? Am I going too fast? Everybody happy? All right, so, and now you need to make progress while you compare it with this key. And now you have to do 3 cases. You know, if it's equal, you're done. Or otherwise, you go to the left or you go to the right. Right? So that's pretty straightforward. Oh, somebody, I thought I had slides for it, but I guess I don't. Somebody at one point complained to me, why do we have equals on both of these here? Could I say, if it's less than or equal to, it has to be over here, and if it's greater or equal to, it has to... First off, could we have non-equals on both of them? Everybody smaller over there, everybody bigger over there? Why not?
Equal.
Right, we have a bunch of the same numbers. All right, so now, could we have them on, put the equals on that side and not on this side? Would that be okay? What's going to be a problem?
The tree will not be balanced.
Yeah, if they're all the same, if they were all 25s, then you couldn't balance the tree. Very good. All right. All right, so I'm afraid that we always get to this before I think about it. And I wish I had a deck of cards, but I always forget to bring my deck of cards. Anybody have a deck of cards? You know, I've taught this enough times that there was a time somebody actually pulled out a deck of cards.
I usually carry one, but
all right, just as well. We'll do the magic here. I do some magic and everybody's awed. All right. All right. So let's go through and see what the magic is. As I have these cards and I lay them out face up so that this guy here can see them, and I get him to pick one, and he chooses one card without showing me which card it is. All right. You know this?
James Elvig did this in 2011. He took your slides and did the card check.
Fair enough. Fair enough. They're my slides. I can prove it. That's my son.
It says his name on the bottom of them.
It does. I know. I've seen that. I've complained about that. In fact, many of his slides are mine. I've flipped through his slides. But it's okay. I just want people using them. Anybody can use my slides. All right, so for those who haven't seen it yet, somebody picks a card, and I have a loop invariant. The loop invariant says one of these cards is his card, right? I don't know which one, but one of them is. Everybody with me here? He has a card in mind. All I know is it's one of these cards, right? So I ask him, which column is it in? He tells me it's in the left column, so I now know it's one of these cards. Right? And then I pick up the piles and I lay them out again, and first I put quickly do a shift. My hands are so fast. So fast. Actually, you joke, you laugh here, but let me tell you something amazing. I was in Thailand, and I recommend Thailand. Thailand is so nice. So nice. And some guy was doing this ring trick, and he was magic. I'm just stunned by this guy. He's hooking rings and unhooking rings. And he told me he would tell me the trick if I promised to buy the rings from him, right? And it was only $5 or something, so whatever, right? So I agreed, and he threw in this extra trick where he stuffs this little cloth in, and he pulls the cloth out. And I'm like, and then he shows me the tricks, and they were so dumb. I thought, there's no way I'm going to be able to pull this off on anybody. But you're amazed how stupid people are. I could just fool people. It was really quite incredible. I'll bring them and I'll show you, maybe, if I remember. So all right, so then you reshuffle out the cards and they go in that order, right? Everybody, I know the card is one of those. Now, this is kind of a weird pattern. I don't like this pattern, right? So, is it okay if I color these two green? Right? Well, because in some ways I'm forgetting things. The loop invariant says it's one of those. Well, I'm just loosening it's one of those. Right? And so now I ask him again which column. He says the right column. I know it's one of those. I put it in the middle. I reorder. Right? Now then I ask him again, left column, and then I reorder, and then I pull out the card and everybody's amazed. Everybody got that?
Yeah. It's a very long hand.
What? All right, so the funny things about this card trick, my mom gave my son a book of card tricks, and this was one of them, and my son never got into doing them, but I did. And one thing that was funny is the card trick said two things that surprised me. First it said, this is an amazing trick that nobody knows why it works. Like, what do you mean nobody knows why it works? Second thing they said, which kind of made the first one more correct, is that it only told you to iterate twice. And if you iterate twice, you don't get the right answer. Well, you get the right answer 1 in 3 times. So if they're saying nobody knows why it works, it's because they were right, it doesn't. All right, so anyway, let's, what are we doing here? All right, so we're now going to, yeah?
5 minutes.
Oh, 5 minutes, all right, thank you. Class goes so fast when it's only an hour. My mind, is used to hour and a half or 2 hours or... Anyway, 5 minutes, good, thank you. So this problem, it's called the partition problem, and we're going to need it later on if you haven't used it already. Everybody know quicksort? Right? We need this for quicksort. Anyway, the problem is you have a set of numbers and you have a pivot. Right? And the goal is to partition the numbers so everybody's smaller than the pivot, everybody bigger than the pivot in the pivot. Right? So we need a loop invariant. We're going to, and the joy of this is an easy algorithm, right? You go through the numbers, you throw it in the left bucket, the right bucket. Right? I mean, the algorithm is stupid. But we want it to be fast. Right? The key here is to really be fast. You know those little 3x3 squares where there's one number missing and you have to move them around? Yeah, that's what we're going to do here. Right? You really don't want to move things more often than you need to. So our loop invariant says, well, where do we put things? Right? Well, everybody we've decided already is smaller than the pivot will be over here. Everybody bigger than the pivot will be over here. And everybody we haven't decided will be in the middle. Except we're going to have a hole. And the hole will either be here or will be here. Right? Everybody get the loop invariant? I mean, you need to decide. Your loop invariant just says where things are going to be and what you've done so far. So, and our progress is how many things left to be done. Now we need to maintain the loop invariant. All right, so if we're sitting here, how are we going to make progress while maintaining the loop invariant? We compare this to one of our numbers and we throw it in one of the buckets. Right? Which one should we compare it to? 25? All right, if we compare it to 25 and it's smaller, what do we do with the 25? We put it over here and that gives us a hole here and we're good. Right? But what happens if the 25 is actually a 90? Then what do we do with it?
Swap.
And we have to swap, right? That's work. I don't want to work. All right, so instead, let's compare it with the 14. Right? We compare it with the 14, and it's smaller. So what do we do with it? We just put it in the hole. Right? Did we maintain our loop invariant? Right? Because now the hole just happens to be on the other side. Right? All right, so here are the 4 cases. The hole's over here. You compare it with the 14. And if it's smaller, you put it in the hole, which maintains the loop invariant. Right? On the other hand, if it's bigger, what do? We just leave it there. Right? Similarly, if the hole's on this side, we compare it with the 14. And if it's smaller, we just leave it there. And if it's bigger, we put it in the hole. Isn't that nice? So we just do it. How do you establish the beginning? You just there's nothing there, and there's a hole. And then bang, it happens. And in the end, everything's here and here, and you got a hole in the middle. Which is really nice because what do you do with the hole? You put the pivot in it. All right? And so the key of this is it's really fast. And, right, so if you want to trace it out, you can trace it out. And since we've run out of time, you can trace it out on your own if you care. All right, everybody good? You're working on the assignments, you're studying hard, you're reading the book, you're looking at the slides, you're enthusiastic. I just looked at the schedule. The test is scheduled for not next Monday, but the Monday after that. By then we'll have well finished loop invariants and the test.